Okay, and our next speaker is Emma de Oña. She's here, ready. Welcome, Emma. And she's going to talk about the galactic outflows in the gamma ray regime. Emma de Oña is coming from DESY, okay? And Emma will let you know after 23 minutes, okay? And good, go ahead. The floor is yours.
Hola. Okay, thanks a lot, and thanks to the organizer for inviting me to give this talk. This is really important for us, the gamma ray community, to be here in the presence of the astronomical community in Spain, especially because next year we're going to have the most sensitive instrument in gamma rays in Cherenkov telescope. And my goal in this talk is to convince you that we're doing really great science, and you can join us and we can do things together. But today I'm going to focus on galactic physics, and in particular galactic outflows. And I want to start with this picture that probably makes you feel more comfortable with, which is the sky in the optical light curve. And here you see the galactic plane. Do we have a pointer? Yeah. It doesn't really work, right? Okay, that's better. So here we have the galactic, you can see the galactic plane, everything looks kind of peaceful, but if you go higher in energies, or shorter in wavelengths, then we go to the X-rays. This is one of the first images Rosita published in the 0.3 to 2.3 keV. And then you start seeing that there is a lot of high energy photons and very energetic things happening in the galaxy, including outflows of very, very large sizes. So we can even move to the higher energies, and now we move into the gamma ray regime, which is defined as energies beyond 100 mega electron volts. And this is the sky as is seen by the Fermi-LAT, the telescope between 10 and 500 giga-electron volts. And what you see here basically is the galactic plane is dominated by a fog of gamma rays, kind of diffuse emission that actually is on top of everything that we see there. We can go even higher energies in the TV regime. This is a combined, This is a combined image made out of two instruments based on two different techniques to the Cherenkov light, with HESS and LASO. There's one of the detectors in LASO between 1 and 25 tera-electron volts. And what we start seeing is that this fog disappears, this diffuse away, and then what we see is the emission of the individual gamma ray sources, the individual of each of the accelerator or the emitters of this very high energy radiation that we observe. And this is actually the range of energy in which I'm going to be speaking about. You can even go a bit higher, even at 100 TeV, beyond 100 TeV, and this is what we call the PV regime, and this is 10 to the 15 electron volt, and this is really extreme accelerators. And here, even, this is very recent results by the LASO experiment, and then you see that even at these energies, we even have more than 50 sources, which is still bright up to PV energies. So this is really outbreaking. And well, how do we reach these energies? Now I have to introduce very quick the Hillas plot. There is no gamma ray talk without the Hillas plot. And this is very simple and very powerful way to understand what kind of population, what kind of sources can accelerate gamma rays. And here basically what we have is the magnetic field and the size for a given outflow speed. And this is a very, very basic concept. It means you need to accelerate the maximum energy you can reach. You can balance. You can look by balance the time you need to reach. The time you need to accelerate a particle in a given electromagnetic field before they. Sorry. Okay. So basically, you need to accelerate the particles to certain energies before they escape the source you have. So basically, you put these two things together, and that gives you the maximum energy you can reach in a source with a given outflow velocity, with a given size, and with a given magnetic field. And this is very simple. This is unnecessary. That doesn't mean you're going to have gamma rays, but this is a necessary condition to really reach these energies. So you can just get all the population of galactic sources and put it here for typical magnetic fields at typical size, and then you see if you can actually go and accelerate. This is a line for 1 PV, for the speed of light, and it tells you if you can actually reach TeV, PV energies in these objects. And then you can have things like neutron stars, which are very small. We have like at the order of kilometers, into the 3 kilometers, and then, but this, you have extremely high magnetic field. So you are actually here. So that means potentially you can accelerate particles to this maximum energy and create and produce gamma rays. And then you have things like supernova remnants or pulsar nebulae or stellar clusters in which the magnetic field might not be that high. You need microgauss, milligauss, but they are so large, up to 100 parsecs, that you could still actually explain many of these gamma ray radiation that we see by looking at these guys. So let me go back to my galactic outflows, my sky in the TV, and I want to just show what are the sources that we actually see. So I'm focusing here in this region, which is where the Vela supernova remnant. This is again an image of Rosita, and I chose it because you here have most of the two populations that we have the largest number of gamma rays, and this is supernova remnants. We have the Vela supernova remnants. This is Vela Junior and the Puppis A. And we also have the pulsar wind nebula. We have a bright pulsar, which is Vela, with a very bright pulsar wind nebulae, which is this blue thing, all these blue lines that you see here. This is the high energy emission in X-rays. So this high energy emission tells you what we can see actually in gamma rays. And we indeed look at these things, and then we see a lot of shell-like supernova remnants, like this guy, in which we actually can distinguish the morphology of the remnant and see the shock and how the particles are accelerated here and producing gamma rays. And we also see pulsar wind nebula. This is an image of this region obtained by the Hess telescope. So even if we look at this region very carefully with deep observations, then we have here Chandra, the pulsar, which is around here. This is an image of the Chandra, of the Chandra telescope in the Vela pulsar. And when we look carefully to this guy, we actually see a point-like source on top of the pulsar. And we do the timing analysis of these photons, and then we fold it with the period of the pulsar. We see that the photons come at the right rotational phase. So we actually know that there's also gamma rays above 5 TeV coming for the pulsar itself. But this is not the only things that we see. As I said, this is very rich right now. We have many things. We have microquasar. This is the case of SS43, which is a galactic black hole in which we see actually the jets, these ultra-relativistic jets. We also see non-relativistic shock besides supernova remnants, and we had the detection of the first novae, RS of Euclid, a couple of years ago. And then we see in general many objects or many populations that has to do with massive stars with fast winds. And this is either stars in compact objects, in binary systems with compact objects, or two stars together, or a group of stars in the collective effect of the wind and creating a big bubble and filling up with high energy particles. So how do we create, how these shocks actually produce gamma rays? This is in the TV regime, there's basically two kind of competing mechanisms. You have the acceleration here, somewhere in the shock, and you can accelerate electrons and you can accelerate protons or heavier nuclei. So if there is electrons, you basically, in the presence of magnetic field, you're going to have synchrotron radiation in the low energy band, and these high energy electrons will upscatter in photons to high energies and appear in the inverse. And that's why for us it's really important to have multi-wavelength observation on this, on all the wave bands to understand what's actually happening in the source. You can also have protons or hadrons, and then we have proton-proton interactions. You have protons accelerated in the shocks, and then you have some matter, some clouds there, and these protons, they interact inelastically with this matter and produce pions, and these pions, they decay, the neutral pions decay in gamma-gamma, and then you will have something as gamma rays at the level between GeV and MEV and TeV. And how do we detect these gamma rays? But fortunately, this high radiation is filtered by the atmosphere. So basically, if we want to detect these gamma rays, we have to go up in the atmosphere, and then you basically put in your satellite, put a tracker and a calorimeter, and you detect the gamma rays, and then or the photon, and you collect it and digitalize and so on. But when we go to the very high energies, and this is the TV, it's really difficult, it gets really expensive to put this tracker on space. So what do we actually do is we use the atmosphere as a part of our detector. So here, then you have the same thing, but the atmosphere will be our tracker and calorimeter. So you have the photon coming into the atmosphere, producing an electromagnetic shower. Basically, the photon falls and creates a pair of electrons, positrons, and you create a shower of particles. So we basically can, to detect these particles that are falling onto us in a big area, basically what we do, these particles, when they travel faster than the speed of the light in the medium, in this case the air, then they produce a fast flash of Cherenkov radiation, which is ultraviolet light and is very, very thin. It's a nanosecond. So you need an array of big mirrors, arrays of telescopes with large mirrors. You focus this ultraviolet light on fast cameras, and you get your signal. So this is very effective, and then which is what we call the imaging atmospheric Cherenkov telescopes. But you can have the same different technique if the particles, if the photon is really energetic, the particles can actually reach the ground. And then there you can put some water. Instead of using the Cherenkov light on the air, you produce the Cherenkov light on water. And then you have that kind of tanks full with water, and you can just observe these very high energies like this, or detecting directly the electrons and positron and charged particles with scintillators. So this is what we have right now around the world. We have three big installation array of telescopes. They are similar. They are all very powerful instruments. They have different configurations. Depends. Some of them they are more focused on low energies, more in the high energies. In the north, we have MAGIC, that you probably know very well because it's in La Palma, and we have Veritas in North America, and we have HES, which is in the south hemisphere. And right now, we have the first prototype, LST-1, of the CTAO observatory. And I'll speak about this in a couple of minutes. But I just want to also mention these two big experiments which are in Mexico, in HAWK, which is this water Cherenkov telescope, and LASSO, which is an hybrid, and they're producing really, really interesting results for above 100 TeV. So in the TV regime, I just want to focus on these three guys because we have a lot of results, a lot of cool things to show, but this is three things that I want to speak, and basically the ultra-relativistic outflows and relativistic outflows. So let me start with pulsars or with neutron stars, and we already heard a lot of pulsars yesterday, and magnetosphere just by Beatriz, so I'm going to just not explain how a pulsar works. So basically, you have a very magnetized rotating star with an extremely high magnetic field, but you can produce photons at several places within this magnetosphere, so kind of everything is frozen there. You have some kind of gaps, you accelerate electrons, positrons, and then you produce this pulse emission. You could have potentially pulse emission in the ultra-relativistic wind. This is where this kind of sheet that she was also showing in a different scale of magnetic field, but you have this ultra-relativistic wind, which might also be stripped because of the movement of the pulsar, and then you also might get some pulsation there, or the nebula, but the nebula you would expect some steady emission in phase approximation. And indeed, these pulsars are really, really efficient in producing gamma rays. Here, I put again the sky by LAT, and then you see the three of the brightest source in the LAT sky are actually pulsar. This is Geminga pulsar, Crab, and Vela, and the emission is so high that goes on top of this fog that I showed before. But those not are the only ones. LAT has actually detected many of them, and it's a very rich phenomenology, and the data set of the LAT right now is amazing. But for us TV astronomers, there is a bit of a problem. When you look at the spectrum, this is the energy spectrum, this is the typical synchrocurvature radiation because it has magnetic field, very high magnetic field, but when you get to a few GeV, there is a very drastic drop-off flux. And this is the typical sensitivity for Cherenkov telescope. So it makes it really difficult for us to study pulsars. But we still, anyways, continue trying to get the signal from these guys. And we actually now we have 4 detections of pulsars. This 1706, Vela, Geminga, and Crab. And when we look at the spectrum, there comes a lot of surprises. First of all, we start seeing tails. And when tails mean this is, again, the Fermi emission, when you expect it to go down. But what we actually see is that it doesn't go down, but it continues to high energy with a power law. So something is happening there which we don't actually understand. And it doesn't really follow the kind of physics, simple physics we think it is. And even in the case of Vela, which is this guy here, what we see is that it's not just going down, but then you have a new component which reaches up to 20 tera-electron volts. So, and when we do the light curve, as I spoke before, this is again Fermi. So this is a Hess in the low energy, but the high energy this is beyond 5 TeV, and we see the emission is focused here in the rotational period of the P2, and it really reaches very, very, very high energies. So how do we explain this? It's very difficult. There's not a simple answer to this problem. We know this is what we measure with Hess, these colored bands. This is, again, the points by Fermi. And then what we know is this has to be inverse quantum. There is no other way around. And it has to be, for that, to reach 20 TeV, you need to get something like 4.10⁷ Lorentz factors in particles. So to get this, you can say, OK, let's just compare. And because they have the same rotational light curve, then we can just say, OK, let's just assume that the same electrons are responsible of this part and of this part. So you can assume this is curvature radiation, which is the standard interpretation. You have curvature radiation within the magnetosphere, and then it would be the inverse quantum. But then when we look at this and we try to fit the TeV data, we actually short. We don't really reach. And to actually reach this energy, we need to get this kind of gaps in which the particles are accelerated beyond the magnetosphere. So you have to go at least 20 times the light cylinder, which is the size of the magnetosphere, to really explain this. So this is still to be really understand what's going on here. We can also say, OK, this happens outside the magnetosphere. Then you have this kind of strip wind, and then you have synchrotron radiation. Then the magnetic field can be much reduced. I do synchrotron radiation here and inverse quantum, but then you're even shorter. This is kind of solved if we think that something that you have a wind, which is ultra-relativistic, and it's got a gamma of around 5, but then again, you have to go a bit far away, too far maybe to explain the light curve. So this is something, an open problem that we're still working and trying to find more about it. Another compact object with outflows, with relativistic outflows, is this famous Manatee Nebula, SS433. We had the black hole here. And the black hole has this kind of the jets which are precessing up to 0.1 parsecs, then they kind of disappear, and they reappear later around 25 parsecs. And this is when you see these huge outflows, which fill up all these nebula up to 100 parsecs. So we actually look at this guy for around 100 hours, and this is, again, the nebula in radio and low wavelengths. And the X-rays, this is here, you have the black hole from which we don't see emission. And this is the hard X-rays. And what we actually see, when we look at the emission, the gamma ray emission at different energy bands, is that you have the maximum of energy in the shock, when the jet reappeared, and then the emission goes down. So basically, the high energy emission, the photons are closer to the black hole. And this is actually understood as there is something, basically the jets are launched with 1/4 of the speed of light, and then they reach something, and this is like an electron trap. You just trap them there and make it slow, and we could just model this and get a velocity of 0.08, and then this is where all the particles are accelerated, and in this you create this shock. and then this electron should be accelerated at least to 200 TeV. So that is the first one, the first time that we detect a microquasar. And the most interesting thing is it tells you how efficient these guys are also to accelerate and produce gamma rays. And there are actually several of them coming up in the summit conference. The last example I want to show is the NOVI. NOVI are nuclear explosion. You have like a compact object, so a white dwarf, and with some bright, big red giant star, which is accreting, which is accreting matter over the white dwarf until the pressure is too high, and then you have a nuclear explosion. And this nuclear explosion produces a huge shock very fast. You can reach velocities between 400 and 5,000 kilometers per second, and the kinetic energy is also high enough. Those guys have been detected up to now by Fermi with GeV satellites, but they were never detected, and they were not really thought to be so energetic to produce TeV gamma rays. So we look at this guy, RSF, which actually went upwards. This is like the historical light curve of RSF since 1930, and we look at it in the outburst from happens in the middle of August in a couple of years ago in 2021. We saw an alert from Fermi with a very high ejecta velocity of 2,600 kilometers per second with very bright, and then we look at this guy and we actually detect it. And we saw a very interesting behavior. This is basically the light curve, the energy flux over time. So this is where we got the trigger, and then Fermi went up at the maximum and then went down, declined, the flux declined. And what we actually saw is the flux goes up a couple of days later, and then you have the maximum, and then it goes down up to, this is what time that we couldn't observe, we re-observe later, and it actually follows the same trend that we saw in LAT. So basically, this is what is happening. There are just 2 days, in 9th of August and the 13th of August in orange. And we basically see is the high energy in the GeV regime, that you have the peak, and which you can observe here, and then as the day passes, the emission in the GeV goes down, but it becomes harder at the high energy. And this is, we believe it is because the hadrons, the protons, they need some time to actually reach the maximum energy that we see, which is around 10 TeV in protons. And this is it's the first time that we detect these guys, and these probably protons, and then we also can prove there is acceleration of protons of this guy up to 10% efficiency, which is pretty high for this kind of shocks. And that also tell us a lot how a shock behaves. We always study shocks in supernova remnant, but here for the first time we could see a shock evolution in real time. So, and something very also interesting that I didn't say is that's what detected. Everyone was looking at it, MAGIC, MAGIC and HES, but also the LST1 was looking at it, and they actually detected. It's a very nice result, and this is the result by the LST1, and the LST1 is the first prototype that we have in La Palma as part of the Cherenkov telescope array observatory. So this is a beautiful instrument, and it's located now in La Palma. This is which is as a part of this observatory, which we foresee. So we are building it right now. We have one site in the north in La Palma, which will have four of these large-sized telescopes and 9 of the MST telescopes. And then we have another one in the south, near Paranal, in which we will have different MSTs and in a larger array, what we call the SSTs, which is a small-sized telescope. And this configuration has to do with the kind of energy in which you want to actually focus. This could be more in the extragalactic light, just in the lower energies, in decreasing the energy threshold. And this guy would be more for galactic science and just looking into the PV sky. And for that, we said we use these 3 types of telescope, the LSTs, which have 45 meters, the MSTs, which were 27 meters, and the small-sized telescopes, which are not that small, they are 9 meters. So this is a photo that they sent me a couple of weeks ago. This is how it looks right now in La Palma. This is the LST1, but the LST2, 3, and 4, they're already being built right now. So, by next year, we hope to have everything ready, including probably the starting construction of the first MST. And there is also a large Spanish contribution. And this is really important, I think, for the Spanish community to know that we have this fantastic instrument, which will be, as I said, the most sensitive Cherenkov instrument in the world by 2025. There's been a lot of contributions here these days, and also tomorrow. There's been first science with LST and some general one, and transient TV astronomy by Paul and Alicia. And this is a lot of galactic contribution. There's already from the LST taking data and getting very, very high quality results on novae, on pulsars, on protostar, pivotron, massive stellar clusters. And also, if you're interested in extragalactic science, this is a fantastic instrument for extragalactic science, for following BLX, quasars, and blazars, and you can just look at this contribution here. And something that I want to just mention, this is the access to the CTAO data. So this is thought we want to have an open observatory. That means a proposal-driven observatory in which 37% will be open time, but the host countries will get 20% guaranteed time. And actually, we are the host, one of the host countries. So that gives us really a great opportunity to do multi-wavelength observation, to work with us, and to get the best out of and exploit and get the best out of this instrument. This is just a glimpse of what we expect to observe when you do galactic science. This is the result we get with HES. Here is the galactic latitude and galactic longitude. The galactic center is here, and this is all. This is the region I showed you before from the Vela Junior and Vela X, and this is all the sources that we see right now. But with CTA, we expect to see something like that, and this is really a wealth of new physics and new data that we expect to detect with the CTA. So I get to my final remarks. I hope I convinced you that we are really doing, we are not particle physics anymore, but we are right now doing kind of astrophysics. And I'm convinced in the next years, CTA will be bringing most of the interesting results in the field, on the field of astrophysics. And just let me emphasize again, the north side will be in La Palma, so let's use it. Thank you very much.
Okay, thanks a lot, Emma. It was a very nice talk. We have some time for questions. Who wants to be the first? Yeah. Okay, I have a question. Yeah, referring to SS433, that is very impressive. The image. I mean, it's not a very particular micro-quasar, in fact, because it's not ultra-relativistic. The velocities that you have reported are between 0.25 Z and even 0.1 Z, more or less. In fact, my question relates to the fact: do you see any kind of relativistic effect in the position of the knots when you compare the west one or east one, the knots that are in the eastern side or the western side? There is a correspondence between 1 and 2 and 2. I don't see. Let me ask you whether there are some differences between these knots.
No, actually, we don't see much difference between the two sides. We see the two sides, but the velocities that we can infer, they are actually pretty similar. So we are reobserving now, and I see Veritas is also reobserving. We're trying to put everything together to see if we can just get. But of course, this is a weak source for us. Yeah. We detect it after 100 hours, which takes 100 hours. So, and it's very, very close to a very bright source, but we didn't see many difference between the two sides. But this is a very interesting effect indeed.
Okay, thanks.
So, thanks, Emma. I have a question on the acceleration of particles. So now that you show that also novae and all these pulsar wind nebulae can also accelerate, has it changed our picture that supernova remnants are the main cosmic ray accelerators in the universe or in the galaxy? What could you comment on that?
You are not the right person to answer because I don't believe these supernovas are the sources of cosmic rays.
Okay, so I would like to know your opinion.
I think it's more clear that supernova remnants, they are indeed the source of the bulk of cosmic rays. They are the most efficient way to accelerate cosmic rays, heavy cosmic rays in the GeV. Then when you go into the PeV regime, we don't see many of the supernovae reaching these high energies. And then we start to see a lot of new population of sources which are actually PEV emitters, which are not supernova remnants. It doesn't mean those guys, they might be one or two, but I think the general idea right now is that you might have contribution of different population of galactic sources to the cosmic rays, here, including stellar clusters and winds of massive stars.
Okay, so which comes to my second question. How long will it take the CTAO to take a really very deep, let's say 1 order of magnitude deeper than current surveys of the galactic planes and search for all these cosmic ray accelerators to maybe do population synthesis and come to an answer? Do you have, well, the CTA has some estimates or ideas?
You mean how long we will take to have an answer to this kind of
No,
questions?
I mean, how many, let's put it, how many years will it take to do a deep survey that will go, let's say, one order of magnitude below what the current sensitivities?
I think, well, to get a survey, our plan, I mean, for next year already, this site will be more sensitive than everything that is around. We still need some time to build the one in the south, which is when we're going to do the survey. But the survey, basically, we have like 10 years, 3 years that we expect to devote just for the survey, and there we should have like way more sensitive than, or 10 times more sensitive what it has done in 10 years.
Thanks.
Okay, just one last question.
One quick question. Is there any project ongoing or planned to have like an extragalactic survey in the zone of avoidance with these instruments?
Yeah, I mean, there is something maybe I didn't mention, but it's interesting to say. We, as a collaboration, we have what we call the key science projects. The key science projects is 40% is for in-kind contribution from people who are building the telescope, and we have science projects which are what we consider key, or this is kind of for the community, for the astrophysics. They need the expertise of the community. One of these key science projects is indeed an extragalactic survey. So it's to get 1/4 of the sky and do kind of not shallow, maybe shallower than the galactic plane, but really look into to do a census of the extragalactic part of the sky.
I mean, specifically in the zone of avoidance where we have a problem with the ground-based telescopes.
We will.
And
We were going to have one array on the south and one array on the north. So in principle, we should be able to cover the north and south hemisphere.
Okay, thanks, Emma.